Hello everyone, welcome to the lecture on maintenance and repair of concrete structures. I am Sri Priya, I have recently completed my PhD. Today I am going to discuss about the residual service life estimation of reinforced concrete structures. What we see here is the brief outline of the presentation. First I will be discussing the principles of service life design, so various models available and how to do the residual service life estimation. What are the approaches that need to be taken in case of chloride induced corrosion and carbonation induced corrosion. Can you identify this bridge? See carefully. This is the famous Morandi Viaduct bridge in Italy. It is an iconic structure named after its structural designer. It is a cable stayed bridge with two cables on each side of the pylon. If you go into the structural details, it is approximately about 200-meter span, and the cables are encapsulated by prestressed concrete instead of usual metally woven cables. This is an innovative design and it has obtained many accolades for its lightweight and new type of design. But what happened to this structure after 40 years of construction? You can see here the deck has fallen down, the bridge collapsed, then the condition of the bridge was assessed. Here you can see at the top of the pylon a lot of corrosion that happened, which led to the reduction in the structural capacity. The corrosion of the cables and lack of maintenance were identified as the major cause of collapse. This is not only the case in other countries, we have similar kind of bridge collapses in India too. These are the recent bridge collapses that happened in 2018 and 2019, the Andheri pedestrian bridge collapse, Siliguri bridge collapse in West Bengal, Junagadh bridge collapse in Gujarat, Kolkata bridge collapse claiming lot of lives and huge economic loss. So, why such kind of failures occur? It is high time to introspect such kind of failures and learn from these failures. What we learn from these failures? Adequate knowledge about the interaction of materials and environment is lacking during the design phase, leading to the poor choice of materials. Even in the previous case of Morandi bridge, you can see that the designer has chosen prestressed concrete to avoid premature corrosion, but the interaction of the concrete with the environment was not considered sufficiently. This led to the poor choice of material and led to final collapse of the structure. Second is the codal provision for durability design are not implemented at site properly. For example, if some cover has to be given according to the code, the minimum cover is only provided. In case of structural loads, we are giving sufficient factor of safety and then consider that for design. But in case of materials, if we are giving the factor of safety for durability based design, then these kind of cover and low water cement ratio are not implemented at site due to poor site practices. The third and foremost important thing is periodic preventive maintenance. This is not in place in many of the structures. Lack of expertise in data collection and interpretation is also prevalent. In today's field, if you go to any kind of field, the data interpretation is very difficult because of the lack of expertise, and there is no record for repair and failure histories. So, to avoid such kind of premature deterioration, durability based design and periodic maintenance should be adopted. To understand more what is meant by durability based design, we will dig deeper. Designing the structures giving importance to environmental loads in addition to structural loads is called durability based design. So, now the question arises, what is meant by environmental loads? For example, if we have earthquake and wind, then these are called environmental loads and they are taken adequately care by the codal provisions. with the probability of occurrence once in 50 years or once in 100 years. But if we take chloride spray, carbonation etc., which are daily changes, and freeze and thaw like seasonal variations, these environmental loads are not considered adequately, and these are also subjected to huge variation because of the change in climate conditions, example global warming. So, what happens when such loads are not considered? If these loads are not considered, then the materials start deteriorating prematurely. If this continue to happen, then the structures do not serve its intended purpose, leading to huge economic loss. So, the durability based design enhances the service life of structures. Now, we will see what is meant by service life. Service life is the time during which the structure is able to meet the requirements of the user safely without any repair or any intervention. For example, this is the age of the structure and this is the damage level. This is the structural element considered. So, from the construction to the initiation of corrosion, this is called corrosion initiation phase, and once the corrosion starts, this is called propagation phase. The structural element, if we take this, chlorides or carbonation from outer surface enter through the cover concrete and reaches the surface of the steel, leading to the initiation of corrosion. So, in case of corrosion, there are only two major types that are being considered. One is chloride induced corrosion and another one is carbonation induced corrosion. So, chlorides or carbonation enter from the cover concrete and reaches the steel, and we are talking about the cover concrete of 2 inch. So, if we have to design a structure for 100 years, then we have to consider the ingress of fluoride or carbonation for the 2 inch cover with 100 years. So, that is the challenge that exists in the service life. So, to enhance the service life, understanding the durability characteristics of the materials is essential. So, the first and foremost principle of durability based design is all materials deteriorate with time. Every material deteriorates at a unique rate. For example, if you take concrete, concrete reacts with environmental exposure in a different way than that of steel. So, each material deteriorates at a unique rate, and the deterioration rate also depends on the environmental exposure condition. Material protective systems, for example, if you want to prevent carbonation from happening in concrete, you can have a anti-carbonation coating. And then the durability properties of the concrete. For example, if you use a supplementary cementitious based concrete, then there will be a greater resistance towards the ingress of deleterious agents than the normal concrete. So, all these impact the service life. So, these systems can be considered for designing the new structure, but we have lot of existing structures. So, how to ensure the longevity of such existing structures? For that, we have to calculate the residual service life. The residual service life is the remaining time from now to the corrosion initiation, that is during which the structure meets the user requirements safely. For example, if this is the age of the structure that is being considered and this is the initiation time that is being estimated, then the remaining life, which is the corrosion free life, can be estimated from the initiation by subtracting the initiation years from the age of the structure. So, why this is important? Because this will help us to schedule the preventive maintenance. Now, we will move on to chloride induced corrosion. So, if you have to model the ingress of the chlorides in this cover depth, then we can use the Fick's second law of diffusion to simulate the chloride ingress. You can see here that this is OPC and this is ACM based concrete. So, once you have ACM based concrete, for the same depth the chloride amount differs hugely. So, this is because of the resistance that is being developed. Also, you have to note that With SEM based concretes, concrete hydrates in a slower rate leading to a value called M, that is the aging factor. So, for all the SEM based concretes, that will be a greater M than that of the control mix, that is the OPC concrete. So, these parameters should be considered in this equation before estimating the service life. So, many models are available which uses the fixed second law of diffusion, and here you can see that there are plenty of models available: square root of time, Life 365, Duracrete, Klinkong, Clodiff, etc. But obtaining realistic input parameters is the major challenge, so that this will closely relate to the realistic service life. So, these are the different parameters that has to be considered in case of chloride induced corrosion. So, there are three major parameters: one is related to material, second is related to design, and third is related to environmental exposure condition. In case of material parameters, that is apparent diffusion coefficient, that is the rate at which the chloride is ingressing; critical chloride threshold value, that is the amount of chlorides that are required at the steel interface to initiate corrosion. This depends on the combination of steel and binder, and the corrosion rate if we are considering the propagation phase also. In case of design parameter, we will majorly consider the cover depth. In case of environmental exposure condition, the surface chloride and the build-up rate are important. Once you have these parameters, if you have to estimate the residual service life, you can take the structure. Here I have taken a 6-year-old bridge, I have taken the girder. So, this is the background information of the girder. It has a M60 concrete with 27% class of fly ash and 0.42 water binder ratio. If we take the core of the concrete, we can layer the core and take the chloride concentration by doing a chloride analysis. Once you get these points, you can fit a curve, and with this you can get the DCL. This DCL will be the DCL at the age of the structure. In this case, we have taken 6-year-old bridge. So, this is the DCL at 6 years, but all the service life estimation considers DCL at the age of 28 days. So, we have some equations and we can back calculate DCL 28 from DCL 6 years. Similarly, with this bit you can also do a calculation for M, that is the aging coefficient. So, the first topmost layer you can consider for surface chloride concentration, and then the exposure condition for the chloride build-up rate. So, the next parameter we need to know is chloride threshold. This can be determined by HRACT method. Here you can see this is a lollipop specimen, this is the rebar that has been used with a mortar specimen, which is similar to the composition as that of the binder in the concrete. So, you can do a repeated RP measurement with this 3 electrode system, and then with the corrosion initiation criteria you can find the chloride threshold for different types of concrete. You can see that the different types of concrete has different types of different values for chloride threshold, even though the steel is same. You can see get the further details of this experiment in the previous lecture. So, now you have all the parameters required for service life estimation. Now, you need a tool. So, this is a Life 365 tool, which is easily available in the internet and easily downloadable. This is the user interface of Life 365. Now, we can take case studies with a consideration that a bridge is along the seashore with SEM based concrete, 15% of silica fume and 15% of fly ash, and then we can consider a conventional steel, cover depth 50 mm and water cement ratio of 0.4 and 0.6. This is the first tab, this is the project tab. Here you can do all the design parameters. You can choose the type of the structure, whether it is a slab and wall. Slab or wall means it is a one dimensional exposure. You can also choose column, which will be a 2-dimensional exposure, then you can also choose different types of concrete that is being fed. If you have 3 different choices, you can feed all the information about the concrete in this. Second is the exposure tab. So, this Life 365 is based mainly for chloride induced corrosion. So, if you can directly choose the location of the structure, from that it will automatically calculate the surface chloride concentration, chloride buildup rate, etc. Or if you have a structure that is already in place, then from that you can set the values here. Similarly, the temperature history also you can either fit the temperature based on the exposure condition, or it will take automatically from the location chosen. The third is the material characteristics. Here you can input what is the type of the steel, what is the DCL at 28 days, M, hydration years, it is usually taken as 25, and then chloride threshold which we found by HRACT, and propagation years. Life 365 by default takes 6 years as propagation years. So, if you want to calculate corrosion free life, then you can make this as 0, and if you have to calculate M, there is a formula given in Life 365 manual that is also easily downloadable from internet. So, from that formula you can calculate the M value, and then when you click calculate service life, it will estimate the service life and give us a cumulative density function. From here you can see that for 50% probability it has given for different types of concrete the initiation years. If you see closely, the control concrete has given only 4.8 years, and other type of concretes has given at least 2 to 3 times increase. So, this emphasizes the idea of using SEM based concrete in sites and also lower water binder ratio. From this you can calculate the residual service life by subtracting the initiation years and the age of the structure. But Life 365 has some limitations, like the calculation of M is very much dependent on the composition, and it restricts the usage of M to only 0.6. So, nowadays we have lot of materials, new materials which are having slower hydration. So, maybe we have to relook at the calculation of M. So, that cannot be accommodated in Life 365. Also, the standard deviation by default is taken as 25%, but in case of field structures the variation will be huge. So, to accommodate these kind of small variations, we have developed a program called SLChlor to estimate the service life. So, this is also based on Fick's second law of diffusion. For here we have taken an example of bridge pier with 70 mm cover depth. So, we have taken 4 different types of concrete and we have estimated the service life. So, here you can see for C1 and C4, even though it is of same grade, it is showing that the age is increased by 4 times. So, this again and again emphasizes that the type of concrete and the water cement ratio that has been used in the concrete plays a major role. So, the diffusion coefficient and the aging coefficient, which indirectly plays a role for type of concrete and water binder ratio, that plays a major role in enhancing the service life than chloride threshold. So, if you are a deciding authority and if you are not of materials background, how will you choose the materials? For that you need to have a user friendly tool which is readily available, like a design chart. To have this kind of design chart, we developed a similar kind of thing called nomogram to estimate the service life. Here you can see the first quadrant, it composed of probability of failure. Here the probability of failure means the corrosion initiation. So, this is called probability of corrosion initiation, and then the cover depth. So, you can, if you say what is the probability of corrosion initiation, if you have a tender document which specifies the service life as 100 years, the probability of corrosion to occur in 100 years is 20%, that means it is 0.2. So, if you have in this example I have taken as 0.2 and the cover depth as 40. So, this will be specified in the code. For the exposure condition, minimum cover depth will be given. So, I have taken that cover depth, and then if you have a choice of material, for example, you can take OPC concrete. So, the OPC concrete is given, and then you have another choice of material, for example 50% slag and fly ash, or OPC with corrosion inhibitor, that is 2. So, you can have 3 choices, that is OPC C1, and then OPC with the inhibitor, that is C2, and then slag, that is C3. For these 3 different types of materials, you can make a concrete and find the respective diffusion coefficient. So, that will be given as D1, D2 and D3. So, once you hit D1, D2, D3, you can go to the left and find out the service life. So, you can choose the materials based on the optimal cost and the service life it is rendering. So, you have a ability to choose the materials based on its performance. So, you can use the nomogram in a reversible way also. So, if you want to have 100 years of service life, then you can, from here you can have a diffusion coefficient. So, you have D1, D2, D3, and then from that you can know what are the different types of materials used. So, you know the C1, C2, C3, and from that you have to go left to understand what is the type of cover depth you want, then from that you will understand the probability of failure. So, these kind of nomograms are also developed for different exposure conditions. For example, this the one I explained is for 800 meters away from sea. Similar nomograms were constructed for structures which are exposed in the splash zone, spray zone, and then 1500 meters away from sea. So, synergistic effect of various parameters must be considered while selecting materials, and these nomograms help us to do that effectively. So, now we will come to carbonation. So, in case of carbonation also there are different parameters that need to be considered. Here also I have categorized into 3 parameters, that is material parameters, design parameters and environmental exposure parameter. In the material parameters we have apparent carbonation coefficient, critical pH value and corrosion rate in case of propagation phase, and design parameter, that is cover depth, and environmental exposure condition, that is carbon dioxide concentration. So, if you take a core from the existing structure and spray phenolphthalein indicator, you know that the because of phenolphthalein the concrete will change its color. So, if it is carbonated, that is if the pH is less than 9, then it will turn as colorless. So, this is the carbonation depth, and this portion is non-carbonated. So, this carbonation is being researched throughout by various researchers, especially for SEM based concrete, because the carbon dioxide concentration is varying from place to place. For example, if CO2 concentration in Madras will be different from Delhi, and if you compare these two, the carbonation rate will be different. Similarly, if you compare India with Singapore, the carbonation rate will be different. So, we have to model such kind of variation in the climatic conditions and generate similar nomograms. So, in IIT Madras we are researching this, and we can expect similar nomograms soon. So, to summarize, the durability based design giving importance to environmental loads is necessary for enhanced service life. The choice of materials should be done after careful consideration of its interaction with the environment. Periodic testing of chloride and carbonation profiles and updating the estimates of residual service life are necessary to prevent undetected corrosion, especially in case of strands which was happened in Morandi duct, and expertise in data collection and interpretation of field structures should be developed, and we should encourage the young researchers to go to this research career. Record of repair and failure history should be done for future reference. In short, balance between steel and concrete should be achieved, that is, the quality of both steel and concrete should be given appropriate care for enhancing the service life. Thank you.